So we were talking about policies for limiting trust on the root. So now we will talk about a different problem, which is how do you limit access for untrusted code, right? So code that you might download from somewhere, or code that is coming from someplace where you don't fully trust the person or the organization that wrote the code. And there are many, so dealing with this kind of untrusted code has been a problem that security researchers have looked at for many, many years. And so we'll talk about various options that are available. Okay, so so let's talk about the one of the oldest mechanisms, which is called chroot or chroot jails. Okay, so the idea is that the chroot is a system call in Unix that changes the root of the file system to a particular directory. So the idea is that if you change the root of a process, then that process will only be able to see the files that are within that that directory. Okay, so this way this process is limited from accessing any file that's outside of this directory. So but chroot itself is a system call that's available only to the root, and therefore in order to do a chroot jail, you have to first start off as a root process, then you have to do a chroot, and then you will relinquish the privilege to not be root anymore, because again, chroot jails are used for untrusted programs, and obviously it would not make sense to run untrusted code with root privilege. So the chroot jails have been popular, but they are somewhat old, and the isolation it offers is somewhat limited because it is only limiting access to the file system, right? So for instance, it doesn't prevent the process from interacting with other processes in the system. And so, it can send a signal to other processes. This may not be something that you want for an untrusted process. So, so it's not a very modern approach, and so there are a number of other alternatives that are available. And one of them is what is called user ID based isolation. It's become very popular in sort of mobile operating systems. So for instance, the way Android works is that for each app that you download, Android basically associates a particular user ID with that app. So every app has its own user ID. And so this means that Android is able to essentially limit each app. It's going to be able to apply a different policy, and the policy basically says what this app can do. And so unlike the model in Linux where the user that runs a process, right? So if you are the user that runs a process, then the process runs with your privileges. Whereas in the case of Android, the app runs with the app's user ID and not with the your user ID. And so this means that each app can be sandboxed to some extent. And in particular, by default, apps are configured so that they can only write and read files that they own, right? So which means that the app has its own set of files that it can read and write, but it cannot really read or write other files. So this kind of isolation makes sure that a single bad application cannot arbitrarily corrupt other applications. So this way, different apps are isolated from each other, and so one bad app cannot corrupt other apps, nor can it corrupt the entire system, because the app will not have permission to change like common directories like /bin or /etc or those places. It also, because things like killing and ptrace and so on, they are all based on user IDs. Therefore, once again, one app will not be able to interfere with another app using these system calls. So user ID based isolation does give you quite a bit, although it's less than perfect, and there are still a few gaps, which is why apps are not fully secure yet, right? And the most common problem that we have with apps is that they are not completely isolated, because often apps want permissions to access your contacts or to access your photos. So there is some common data that that they request access, and they are often given access to, and therefore they can steal this data, and that's one kind of problem. They can also put malicious files in these common places, and such as the photo directory and so on. And once again, through that, they can try to compromise other applications. And again, that's another way in which a malicious app can interfere with other apps. In addition, in Android and on iPhone, there are ways for apps to interact with each other. And these interfaces, again, permit some way for one app to abuse or subvert another app. So again, this user ID based isolation gives you a very good it's a very good improvement over the default Linux model, where everything runs with the user's privilege. So it's definitely a much improved situation as compared to that, but it is still not perfect. So another model is what is called one-way isolation. And the idea of one-way isolation is it is attempting to address one of the problems with the app model, right? Although the concept of one-way isolation goes back to many years before apps, but it still addresses one of the problems with apps, which is that by default, as we said, the files of an app are isolated to that app alone, right? So another app cannot really use these files, which means that it is not easy for two applications to collaborate with each other, right? So whereas on our computers, right, our laptops and desktops, the typical situation is that the applications interact with each other. You drag and drop something from one application to another application, and you expect all of this to work nicely. And so this means that full isolation is going to be a problem. And so the idea that has been proposed is what is called one-way isolation. And the goal of one-way isolation is to protect the integrity of your system. So suppose you download and run some application. This application should not install, say, malware on your system, right? So that can be ensured by preventing this application from really writing anything into the system. Okay. So, but if you just say you can't write anything, then no application is going to work. So the way this is done is that you allow the application to run, but it's going to you allow the application to write, but it is going to write into a private area that no other application is going to look at. Okay. So this way the application can continue to believe that it can write arbitrary files and will continue to work. At the same time, the system itself is protected because all of these changes are being made to some isolated section of the file system where nobody else is going to look at. And therefore, if the operating system is booting up, it's never going to see these files. And so no malware, even if it is written by this untrusted application, is never going to be started up. So this way you get integrity, but of course, because this full one-way isolation doesn't limit the application from reading any data, right? So as a result of that, you are not going to protect confidentiality, but integrity can be protected. Okay, so the last thing that we are going to talk about is a system called sandboxing, a topic that we have already talked about before. So I'm going to sort of very quickly breeze through this in the next few minutes. So we already mentioned seccomp, which is the Linux mechanism for limiting system calls that can be made by a process. Okay, so the original seccomp basically says that you can make only like 4 system calls, right? So you can do read, write, exit, and sig return. Okay, and so this means that for instance, it cannot make a network connection or open a new file or anything like that. So essentially, a sandboxed process cannot really do anything at all. And this is useful if the sandbox is set up properly, right? So for instance, if you have a sandbox for a renderer process in a browser, then this renderer process can continue to do its job. But in many situations, these sandboxes are too restrictive and they are not going to work. So people came up with extensions, and this is called extended seccomp. Seccomp BPF is a more recent version that allows more configurable policies, and we have talked about this before, but still they are limited in the sense that they can only refer to system call name and arguments that are in the register. But most policies that you want to enforce would want to refer to, say, the name of a file that's being opened. But unfortunately, this is not something you can do with seccomp BPF. We have talked about the extended BPF, which is a further extension, and extended BPF has many more features, but it is also much more complex, and it's something that's still in development, but I think it's something that is going to be more useful in the future. But regardless of which system called sandboxing mechanism you use, one of the problems that we have talked about is race conditions involving things like file names. Okay, so even if you have a system called sandbox, the sandbox may check the name of a file before the system call is allowed to proceed, but between the time the sandbox performs the check and the time this file is actually opened, the target could be changed, and now the policy enforcement is then subverted. And so there are, for this reason, none of these system call sandboxes are typically used to enforce policies on files that are accessed. So there are other approaches that people have proposed. One of them is called system call delegation, where the idea is that you're going to instead of trying to enforce a policy on what files can be accessed in the kernel, what you're going to do is you're going to instead delegate this file opening to another process. Okay, so this other process, which is called a delegate, is going to enforce the policy on what files can be opened and what files should not be opened. And so now what happens is that the sandbox process has to send its file open requests to this delegate process. And so the delegate process can now check the request. And since there is no shared memory between the delegate process and the original process, there is no possibility of changing the file name between the time it is checked and it is opened. And so as a result, you can avoid the race condition problem. And what the delegate process does is after it opens the file, then it sends the file descriptor back to the original process. And there is a trick or there is a feature in Linux that allows file descriptors to be transferred from one process to another. And it is this, this feature that enables this delegation approach to succeed. So this is, again, a very interesting way to apply a system call based sandboxing, where you sandbox not only based on the arguments that are in the register, but also information that is in the memory of the process, such as file names and so on. And finally, there is yet another approach that can be used for securing untrusted code, and that is based on information flow. And in fact, when the Biba integrity model was developed in the 70s, people talked about viruses and how one can protect against viruses using these policies. So the basic idea is that you are going to classify untrusted code as having low integrity and benign code as having high integrity. So what you're going to do is you're going to prevent low integrity or untrusted code from writing high integrity files, such as any file that's on the system. Similarly, what you're going to do is you're going to prevent benign code from reading anything untrusted. Okay, so this way, benign code cannot be subverted by, say, a malicious file that some piece of untrusted code left on the system, or a malicious script that untrusted code put somewhere on the system, and so on. So by making sure that benign code can never consume anything untrusted, you can make sure that untrusted code can never influence the behavior of benign code, and therefore it is as if benign code doesn't even know that you have ever run untrusted code on your system, and therefore the integrity of the system can be protected that way. So that's what I wanted to say about untrusted code and the policies for untrusted code.